ভুলে লেগে গেছে।
Yes. We just started the recording. I'm gonna disable the participation notification. And yes, so you have the chat window open. And also the participation list like now. All right. We're starting today's lecture. Last class we did talk about what do we mean by weight and what do we mean by the sensation of weight, or how do we detect weight, and what gives us the feeling of weightlessness. That would be the case. Just to give a small recap, is that we're going to sense our weight not because earth pulls us down, rather because we are going to exert that weight onto a surface or onto air if we fall through air, and the reaction force of that weight that we'll be receiving from another object is what is going to be detected as the sensation of weight in our nervous system, in our body. So whether we sense or not, weight is always there, but whether we are going to sense it or not depends on how much of the weight can we apply on a certain solid surface. If we can apply all of our weight, we're going to get back an equal amount of reaction force. We'll feel all of our weight. If we apply a small part of our weight, we're going to feel lighter. One of the examples to feel partial lighter is whenever we try to swim. I mean, if you are in a water body, you'd feel like that your body becomes light. The reason is that water has a property called buoyancy. Every fluid has a property called buoyancy, and because of its buoyancy property, every fluid tries to push other objects out of itself. I mean, away within the gravitational field. The idea is very simple. If I give you the idea of buoyancy, which is actually a pretty interesting idea, and I might as well discuss about that. So let me just give you an idea of partial weight, and I'll definitely get to your question. So hold your horses. So let's discuss this one. And let's say this is a certain container, and let's say it is filled up with some water. Let's say up to this level. So let's label that water with blue, maybe blue. And oops. Okay, never mind. So let's say this is the water, and that water is labeled as blue. Now, another thing that I need to understand: if we have a solid object, let's say a piece of a ball, ball. Let's say that ball is represented by this circle. Let's say it's a hollow ball that is filled up with air. For filled up with air, a bit smaller would be useful. Now, try to understand: if I take this ball and start pushing this object into the water, what is going to happen?
It's gonna face a force.
It's gonna float.
It will float.
It's gonna face a force.
It will float. Well, it will try to float. Or well, what I was trying to get from your idea ahead is that, I mean, let's say I'm gonna fill this ball with the color, because other than that I cannot make sense with it. So let's say this is the whole ball. So if I now take the ball and put it in and push it all the way down in the water surface, essentially this water volume should rise by a little, because the amount of volume that the ball is going to cover inside the container, that equal amount of volume of water has to be displaced, and the water level will rise by that same volume. Now, what is really important for us to understand that in the process of this volume increase, what is really important for us to understand that in the process of this volume increase, or actually not volume increase, the raised height, this water, which was experiencing its own gravitational force, let's say I'm gonna label this by some arrow. Let's say water is experiencing its own weight. Let me show you that all of this water is experiencing its weight, that is working downwards, and naturally the water will always try to get back to its original position because of the pull of the weight. The only way the water can actually go down to its original position is by pushing out the ball. If the ball is pushed out, and then the water can get back to its original position. So this is one easier way to understand how it actually works, but the actual physical description is a bit different. The physical description is, I'll show you a small video to give you an idea of upthrust. So what is happening over here is that the water amount is going to try to push the ball outwards, which means if we represent the weight of this ball, let's say it's a solid ball, by a certain arrow length of, let's say, brown. Let's say this is the weight of the ball. and because it is pushed into the water, let's say the water pushes this ball using an upward force that is, let's say, has the value of this much. Let's say the water is trying to push it out by this much force. Now I'm showing different length of arrows, trying to give you an idea about the magnitude of the forces. Longer arrow represents bigger force, smaller length arrows represents smaller force. So if this object used to be in air, then this upward force wouldn't exist. If you wonder, well, shouldn't air produce some force? Air might also produce some upthrust. This force is what we call upthrust. The name of this force is upthrust. This is the spelling, upthrust. This is the spelling. So water would produce a much bigger upthrust compared to air. So if we now place a weight machine at this location under this ball, we're gonna be able to measure the weight. That weight would be definitely smaller than the same thing being measured outside the liquid. The only reason is that in this case, part of the weight is being balanced by the upward force available from the water medium. So this ball is gonna now experience a smaller fraction of its weight. So the object is gonna feel lighter. That's one example where in practical cases where we can actually feel lighter. So this is one scenario. For air, we also have an upthrust, to be honest, because whenever we are in atmosphere using our body, we have displaced out the air, displaced out the air to occupy our own volume. So that air is also going to try to occupy that same volume where we are at, and the only way we can do this is to push us out. So this is a theoretical discussion which can help you to remember, but the practical discussion actually works with pressure. Now, before I get into the idea of pressure, do you kids know what pressure is?
Yes, sir.
For
Yes,
those
sir.
of you who do not know what pressure is, because this is a bit later chapter in our syllabus sequence, pressure is mathematically defined by force per unit area. Force per unit area. It has a unit of Newton per meter square. Newton is the unit of force, and area has a unit of meter square, SI unit. So pressure typical unit হচ্ছে Pascal. So Pascal is given by Newton per meter square. This is the formula for pressure. The idea of pressure is this, that how much force do you exert on unit area for any surface. Now, one of the examples that I can give you to make sense with you for the idea of pressure is that one of the idea I can share you to make sense with the idea of pressure is that pressure is basically a determinant for how much fiercely or how much widely you are trying to squish a surface. If I give you some idea, let's say if I mean do you kids ever do you kids know what is snowboarding?
Oh, birdie.
No, sir.
Snowboarding.
Sir.
Yes.
Yes,
Yes.
yes.
I mean, do you guys know the difference between snowboarding and skiing
Yeah.
and skating?
Yes.
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 I mean, skiing and skating are
Nah.
two specific examples which can work really well to transfer the idea of pressure. I mean, many of you might feel as a pressure to অনেক পরের chapter এখন কেন এগুলো নিয়ে হাওয়া করতেছেন? Well, I'm bringing this up. I mean, this is actually a bit far-fetched chapter. I'm bringing this up idea to give you an idea for how the pressure is gonna be involved for the explanation of upthrust. Upthrust, on the other hand, is an important idea for our fourth chapter. It is involved, not essentially covered, but it is involved in the idea parameter. স্যার জনগণের ইচ্ছা যে ব্যাকগ্রাউন্ড পিকটা কার looks like this belongs to a girl. This is the girl from the superstar singer, Secret Superstar. I forgot her name.
Zaira Wasima.
Yeah, that
Zaira
one.
was in,
Yeah,
she
that.
quit Bollywood.
She quit Bollywood.
I think that's good. Karan, she wanted to like focus on like the
Islam.
Quran and everything, Islam and.
I mean, that discussion can be controversial in multiple different aspects. Which different people can have different view. But yeah, she did quit Bollywood, but she's still a beautiful person, I believe. At least she's good looking, because that's why
She's
she's
actually
here.
very pretty.
Yes,
I mean, fame.
I'll give her that. কি বলছিলাম? আচ্ছা, I wanted to show you the difference between
A
snowboarding,
nobody.
skating, and skiing. Okay, so have a look. Snowboarding is this one. This is snowboarding. When you have a sledge like this is a board. Whenever you do rollerboarding basically has wheels underneath, but here you do not have wheels. It's just a uh, slightly carved piece of metal or any or fiber optic surface, and you just get stuck over here, and this is snowboarding. On the other hand, skiing is this, where you have two different pieces of blade for two different pieces of your feet. Whereas skating is this one. This one. They have scissor-like or knife-like edges at the bottom of these shoes, which help them go pretty fast on hard ice. Now, important information, hard ice. So what is actually happening over here? I mean, what is the implication of all of these different information? Now, let me elaborate that idea to you. Snowboarding and skiing, they are both done on soft ice surfaces, like on snow. So basic snow is quite fluffy, so it cannot support the weight of a single person if we apply that entire weight to our surface area of our sole, only the sole that we have for our feet. Which means, I mean, think about it. Let's say if you apply all of the weight to a small area as much our sole on a snow surface, you're gonna get dug up. You're gonna penetrate the snow and you're gonna fall in the snow. And then you'd have to walk out of the snow if you don't use snowboards or ski sledges. In that case, you have to walk like monkey walk. Do you guys know what monkey walk is?
Yes.
No.
No
No.
way, China.
It's good. We're learning a lot of vocabularies.
I just want to make sense and make physics understandable to you. The type of walk that people make bouncy, I mean, both feet up, like there is a good gif. Uh, I don't actually know what to name this, but can I find that GIF? I hope I can. This one. I hope Pinterest allows me to see this. I hope. I hope. Let me see this. This one. Have a look. Did you see what just happened? That guy who ran by.
No.
Okay, have a look. There's this guy coming in.
Oh, I saw.
Oh,
guy
yeah, so.
in a girl
I thought it was a girl.
It
guy
might
in a
actually.
girl
I
costume.
didn't
I
notice
don't
it
know,
at first.
boy or girl, whatever. But the way this person is walking,
That is a
if you
girl.
don't have your ski equipment or snow equipment on your feet, if you are trying to walk on soft snow, this is the how you have to walk through. I mean, you have to lift up every feet and duck through the snow, and eventually have to go on like that. So the reason we are going to penetrate, our feet is going to penetrate through soft snow is because our feet is going to produce enough pressure onto the snow, which the snow cannot uphold. In a very similar way, water cannot hold our body weight. I mean, you can swim in water, by moving your hand and everything, you can float in water. But if you stand vertical try to stand on top of water surface, you're going to simply go down because the water doesn't have that much strength. So that's basically the idea. So the way we can still make ourselves enough mobile onto our water, onto soft snow surfaces, is if we use this kind of long board. So if you think about it, if whenever a person is simply standing on snow, let's say this kid is standing on snow with a small piece of snowboard, what is happening? He's now distributing all of his weight to this large contact surface area. Can you see that? To this large surface area. So now he's producing less pressure onto the snow surface. As a result, the snow is not getting penetrated. It can uphold that person's weight. That's the whole point of having this device, and equally applicable for skiing as well. So whenever the person is actually use this, what are this thing called? Ski. They are called ski, right? Or okay, whenever the person has this attachment in their feet, this boat-like attachment, they are actually distributing all of their weight onto a large amount of snow. As a result, the pressure on the snow surface is less. That's why they are not getting penetrated into the snow. That's the whole point of it. So we're trying to distribute our weight over a large surface area. So if you try to think about the formula that I just wrote, that pressure is given by force by area. Whenever this thing is gonna become bigger, the entire fraction is gonna become smaller, because A is the denominator. So what happens to a denominator if you have what happens to a fraction if the denominator gets bigger? The value of the fraction becomes smaller, right?
Yeah.
So that is essentially what is happening over here. Whereas as for skiing, the scenario is exactly opposite. Skating. Skating is done on hard ice surface. So ice rinks, they are called. So these are like actual ice cube kind of ice, not snow, not fluffy, a smashy kind of thing.
স্যার স্কেটিং করার জন্য তো স্যার স্কেটিং বোর্ডসও তো আছে, সেগুলোর জন্য কি হবে?
Yeah, I'm trying to show you ice skating. Yeah, there is roller skating. For example, this is roller skating.
No, I'm not talking about roller skating. There is also a skating board for those who skate.
I'll look it up.
The surfboard.
I'll look it up. Don't worry. Oh, acha, yeah. These skating boards are basically a mimicked version of snowboarding. If you want to mimic snowboarding on regular hot weather, this is what you can do. You can attach some wheels and you can basically do the whole thing. বুঝে গেছে?
Yes.
Acha.
Yes,
So
sir.
this is another thing. So one of the things that I need to understand, that ice skating is done on hard ice surface, not even snow, hard ice surface. The reason the snowboards, the ice skate shoes, they have a very sharp knife-like edge at the bottom, because whenever the ice is pressured by that small thin area of that blade, at that location of the applied pressure, now you see that other than using our entire feet, we are concentrating all the force through a very small area. So compared to what happened on snow, the exact opposite is achieved over here. On the snow, we applied all of the person's weight over a large surface area so that we would not get in. But in the case of ice skating, we are using a much smaller surface area than the entire shoe. We're applying all of our area through a very small piece of metal edge. So essentially, what is happening? We are concentrating on the force. So the pressure under this metal piece, the contact place where this is, at this point, the contact location at this point, the pressure is extremely high. What this does to water, because water is a very unique material, what this does to ice, that ice at that location of the experienced pressure melts. So, and it produces a very thin film. Film means a very small thickness of substance. It produces a very thin film of water between the ice level and the metal level. As a result, as the person goes forward, that person is basically floating on a thin slice of water. So the water in this case is working as a lubricant, which is readily produced as the person goes forward, because his feet is squeezing onto the ice, and ice has this behavior that when squashed, it can convert into water. Why does that happen? I'm not covering that up. I'm not covering that right now, which we'll eventually see in our thermal classes, but take my word for the time being. So in this case, we are trying to exert high pressure onto hard ice so that we can melt the ice at that location, produce a thin film of water so that we can glide over the ice flawlessly. Whereas in the case of snow, we have to increase our surface area so that we do not get into the snow. Do you understand the difference?
Yes, sir.
Yes, sir.
I mean, does this does the two things make sense?
Yes, sir.
Yes,
Yes,
sir.
sir.
Okay,
Yes, sir.
beautiful.
Yes, sir.
So one other thing that so the reason I talked about this whole pressure thing, because there is another formula that works with for pressure. And if we try to find out the if we try to find out the pressure for liquids, the formula for pressure under liquids is usually given by this formula. This is going to be a bit jumpy question. This is going to be P equals to H rho. This is
H rho G.
H rho G. This is the pressure under a liquid formula. I mean, how this formula comes into existence, I'll show it to you in the pressure chapter. Don't worry. For that, I mean, believe my word. I mean, the implication of this formula is like this. If you have a container that is filled up with liquid, let's say this is a container that is filled up with liquid up to this level. Let me fill this up with some liquid. What kind of liquid? Green liquid. Okay. So this H, although it is labeled as H, this H does not actually mean height. This is the catch. This H actually means depth. Exactly. This H means depth. Now, if I specify a bit more, this means depth from open surface. Now, what do I mean by this? What I'm trying to tell you is that, let me use a different color, that if you are here, let's say at this surface, atmosphere is going to produce some pressure because air is squashing on everything. We have atmospheric pressure. If you start to go from this level downwards, as you are going to go travel into deeper and deeper into the liquid, the depth of those locations, for example, if this location is going to have a depth of this much. This location is going to have a depth of this much. This location is going to have a depth of this much. So the deeper you're going to go, your H is going to increase. So H is not actually height. It actually means the depth of the location where you're trying to measure the pressure. Rho is the density of the liquid and G is a gravitational acceleration. So typically for a single liquid, these two are pretty much constant. So pressure is basically, I mean, largely dependent on the value of H or the depth of the location. The deeper you are going to go, more is going to be the pressure. So H is a so if I show you some mathematical jibber jabber out of this equation, let me just show you one thing. Do you guys know direct proportionality relationship? Let's say if I write an equation, let's say A proportional to B, how can we make this into an equation?
By bringing a constant.
Yeah,
By bringing a constant. So I can write that A equals to
A is equals to K into
K
B.
to B.
K into B. Now this doesn't have to be K, but K is the most common version of a proportionality constant that you use for throughout our math classes and everywhere. So this essentially means one thing. That means that the ratio of A by B is always going to be a fixed number, which also means multiple other information. For different scenarios, for different observation, if you get different values of A's and B's, pair values of A's, A and B's, all of those pair values, if you do the ratio of A value divided by B value, you're gonna end up with the same number. For example, if you for one set of value, if you get A1 and if you get B1, the ratio of these two is gonna be K. For another case, if you find out A2 by B2, I'm saying pair values, which means when the value of A is something different than A1, you get a different value of A2 for a different scenario, and the relevant value for B is B2. That ratio is going to be K as well. So one simpler version that we usually can write when we are working with proportionalities can as well look like this. So I can pretty much write this relationship like this: A1 by B1 equals to A2 by B2 equals to A3 by B3
Equals to a 4 by V4.
yeah, dot. So which means it's going to be proportional. This is the basic idea
But
for converting this into an equation. Now, the point that I want you to understand, we can logically come from here to here. This would essentially mean it should be also logically possible for us to go from here to here. See if it makes sense. What I'm
yes,
saying
sir.
is that if in a certain equation you can determine two variables which are dependent on each other, and if we can find out some sort of constant for the other part, we can say these two variables are going to be directly proportional. That is essentially what is happening over here. Take a good look at this equation. I just
What
say,
if we bring a constant before a?
I mean, if we can pretty much write a constant before a. Let's say if we bring a constant before a, for example, let's say let's say q, random alphabet. In that case, I can also write this thing. I mean, if there is a constant over here before a as well, I can as well write a is gonna be equals to k by q into b. Now, if k is a constant number, q is also a constant number, k by q will also be a constant number. Do you get my point?
Sir. Yes, sir.
Let's say if k has a fixed value of 2 and q has a
I
fixed
don't
value of,
understand.
I'll help you. I'll help you. If k, let's say for a certain scenario, for whenever we're doing this experiment or something like that, let's say the k value was calculated to be 2, exactly 2, integer number 2, and the q value was calculated to be 3. So it means for every cases, 3 multiplied by a should be equal to 2 multiplied by b. Let's say that is the relationship that we somehow derived, which should also mean a can be expressed as 2 by 3 into b, right? Now, 2 is a constant, 3 is also a constant. Now, is 2 by 3 not a constant as well? This is a number. A fraction is also a constant. That's what I'm trying to tell you. Constant doesn't necessarily have to be integer. A fraction is a number which is a fixed value, which is not going to change over time, which is not going to be dependent on other variables. It's a fixed number.
Yes.
So this k by q is also going to be a constant, which means basically a equals to constant into b, which basically means a is directly proportional to b as well. So we can have a lot of different things on other sides, but we can essentially convert what I'm trying to show you over here, what I'm trying to convince you about is that if we have a directly proportional relationship, logically we can convert this into an equation. Similarly, if we have a suitable equation, logically we should be able to convert that into directly proportionality as well. What I mean over here is this. Have a look. In this case, density of the liquid rho is a constant. G is also a constant, which means if I multiply these two variables, this thing is going to be a fixed number. For example, the density of water is 1000 kg per meter cube. Achha, unit apatat matha kamachi na, believe my word that the value of water for density value for water is 1000 and the G value is also, let's say, 10. So if you use this, if you try to calculate the product of these two numbers, this is going to be 10 to the power 1, 2, 3, 4. This value is going to be 10 to the power 4. And this is going to be a fixed value for all sorts of water calculation, which means because this is a constant, I can write this equation into a direct proportional relationship like this. Let's say I can write P proportional to H. So I just got rid of this constant out of this equation and wrote this proportionality equation. Proportionality, not equation, proportionality. Now, do you logically understand how this could be converted into this one? Does it make sense?
Yes, sir.
Yes, yes, sir.
Have a
Yes,
look,
sir.
convince yourself. If you have question, ask
Yes,
me.
sir.
So what I'm trying to mean, the deeper we are going to go into a liquid, the bigger will be the pressure. Now, one of the important parts, please switch off your video feed, whoever just turned it on. I appreciate that. Thank you. So one of the key part that you have to understand that liquid pressure works in all directions. It's not like solid pressure. The solid pressure works on the surface, perpendicular to the surface, but liquid pressure works in all directions. So at this point, I can show you one specific video from Mark Rober. I hope the YouTube does not give me an infringement notice. I actually forgot the actual name of the video, but was it this one?
I'm sitting in a hot tub.
Whoa, whoa.
Because that buoyancy force has been all floating up density of back to my nephews.
density of I think a is the buoyancy force. This happens to be less, force happens to be greater than your force pointing upward.
Exactly.
Bottom, which is a function of the density of the surrounding fluid and the volume of the object itself.
This is Mark Robert.
I'm sitting in a hot tub filled to the brim with solid sand.
Pick up the entire video.
This is one of the coolest things ever. If you take a tub of sand like this and then add air in just the right way, it basically becomes a liquefied soup. In science, this is known as a fluidized bed. It's used in industrial applications such as powder coat painting or in grain silos to make sure that the grain flows smoothly to the outlet. With air on, the top surface is nearly frictionless. It's like an air hockey table. And then when you cut off the air, it freezes everything exactly where it's at. So today I'm going to show you how to make a simple version like this yourself, and then because I became curious what it would feel like to be fully immersed in something like this, we made a hot tub size version. As you can see from this 60-year-old video from the Royal Institute of Science, this demo isn't exactly new. And I've wanted to build one for a long time, but you can find literally no information online on how to make one like that. So I started combing through a bunch of patent drawings for massive industrial-sized fluid beds, and I noticed that instead of one big inlet, they all had a bunch of small holes to deliver the air. So starting with that in mind, it still took us 25 failed versions before we arrived at this design. As you can see, it's just a bunch of half-inch PVC pipes arranged sort of in a ladder. But the key is to drill two 1mm holes 90 degrees apart from each other, and then do a bunch of those spaced 25mm apart. Then you glue all the pipes together and just make sure you orient the holes down so that will keep the sand from getting in. And then you just seal off the container with some hot glue. And then fill your container with either fine sand, or we found glass beads worked really well. And you could power with a small air compressor like this, or you could just rent a large nitrogen container like this for about 30 bucks, and that'll give you 10 minutes of runtime. As usual, I will put a link to all of the parts I used in the build in the video description. So my buddy Ken had an old broken spa in his backyard, which we decided to put to good use. It just stops and you're like locked in place. It's like a weighted blanket on every surface of your body. Now that it was tested and ready, in my ongoing quest to be the favorite uncle, I decided to surprise my nephews with it.
Whoa, whoa.
But before we get to swimming in sand, let's talk about the science behind a fluidized bed. And don't click away if you think science is boring. If you're new here, you should know that my approach to science is similar to velociraptor hunting patterns. I try to bring people in with a catchy thumbnail or a cool thing to see, and then when they least expect it... Clever girl. Admittedly, Okay, the analogy breaks down a little at the end, but if you promise to hang with me for the next 2 minutes, I promise to try and walk the delicate line between trying to make things simple to understand without oversimplifying or being condescending. Fluidization is just when you have enough upward air so that the force of the air pushing on each grain of sand is equal to the downward force of gravity or weight. And when that happens on any individual grain of sand, it hovers in equilibrium like this. You can think of forces acting on an object like a tug of war. And if an object is in equilibrium, that means there's a tie and it doesn't accelerate in either direction, just like in a real tug of war if the sides are even. However, if you add Stone Cold Steve Austin to this side, that will make it totally unbalanced and will start to move this way, which is actually what happens if you accidentally turn the air up too high. And so fluidization occurs in that sweet spot where the sand particles hover in equilibrium, which makes them easy to move around. This is also the reason sometimes you'll see pools pumped with air to cushion the landing for the divers. Now you notice that some stuff floats in the sand and other stuff sinks. This has to do with the buoyancy force, which is a function of the density of the surrounding fluid and the volume of the object itself. Whenever an object exists in a pressure gradient, there are forces from pressure pushing in on all sides, but they push a little bit harder the deeper that you are, which is why it hurts more to be the bottom guy in a dog pile, or it hurts your ears more the deeper you dive in the pool. And this makes sense because the deeper you dive, the more water there is above you pushing down. And if you add up the size and direction of all those arrows, a bunch of stuff cancels out and you're left with one net force pointing upwards. That is the buoyancy force. And if your buoyancy force happens to be greater than your force from gravity, you float. And if your buoyancy force happens to be less than the force from gravity, you sink. Now we usually think of buoyancy with water, but you could think of things like helium balloons being buoyant in our atmosphere. So here's a trick question. Which of these has a higher buoyancy force? It's actually the rubber ball. Buoyancy force has nothing to do with the density of the object, just the volume. So since the rubber ball takes up more space, it has a higher buoyancy force. But you might object, then why does the rubber ball sink and the balloon floats? Remember, it's a tug of war. The rubber ball sinks because the force from gravity on the thick rubber skin and the air inside is bigger than the buoyancy force. But for the balloon, even though it doesn't have as big of a buoyancy force compared to the ball, it still floats up because that buoyancy force is bigger than the weight arrow from the helium and the thin rubber shell. And the helium will keep rising like a ball floating up from deep in a lake, and then it will eventually hang out where the density of the atmosphere is roughly equal to the density of the helium in the balloon, because that's where the tug of war becomes equal. Whew, we made it through. Now back to my nephews.
To move as soon as partner starts to play. Oh no, I can't get it out. Get it! Got it!
Back up!
Christmas is coming, and with the help of Casper,
Okay, the rest of the part is a bit of advertisement from Mark Rober. I'm definitely gonna get a copyright infringement over here, so I'm gonna cut off this part of my lecture, and I'm gonna share that link of this video in the video description, which is gonna be available for you to see anytime you want to see this lecture back again. So, did you understand what actually happened here?
Yes, sir.
So,
Yes.
what is really important for you to understand was this force. I mean, what is the pressure thing? This one. Have a look. This is what this is the important figure that I really want you to appreciate and understand. Have a look. Like I said, that pressure on the whole thing is gonna be Hello? I have to move it frame by frame. Can I move it frame by frame?
Above you pushing down. And if you add up the size and
Exactly. This one. That frame. I want that frame. Excellent. Have a look at this figure. This is an amazingly made figure by Mark Rober. What he did over here, what he's trying to show you that, like I said in the earlier case, that as you go deeper into the liquid level, your pressure is going to increase. And the liquid pressure works in all directions. So have a look at the length of these arrows. This is a square object. So the force is a pressure into area. This is the product. So you have to understand that at a lower depth, let's say on the exact top surface of this object, green object, the pressure is going to be somewhat smaller. As you slowly go deeper down, you're going to have increased pressure. Have a look. These arrow lengths are slowly becoming bigger. You see that? And at the most bottom level, the upward force is pretty large. So all of these forces will be experienced by this object from all the directions. So what is going to be the resultant, which comes right after
size and direction of all.
Have a look at this figure. So this is what we have. Now these horizontal forces are going to perfectly balance out each other because they are just equal in magnitude for the same level in opposite direction. So there is no horizontal resultant force. But if you consider the vertical forces, what you should remember that for the top surface, come on. Why is it so difficult to go to the back frame? Oh. Hello? Yeah, I'm here. I'm trying to get to it. So just if you consider the results, sum of the forces. So he over here added all the forces. These forces perfectly balance each other out, but for the vertical case, the forces do not balance each other out. From downward direction, we have a smaller force, which was working on the top surface. In the bottom surface, the upward forces is slightly bigger. So if you add these two up, ultimately what you're going to be left with?
all those arrows, a bunch of stuff cancels out, and you're left with one net force.
We're going to left out with this one. This is the force that is upthrust. Does the idea make sense now?
Yes, sir.
Yes, sir.
Yes, sir.
It's
Yes,
all
sir.
about the variation of depth. It's all about the variation of depth, because at deeper level we have bigger pressure. Bigger pressure gives us bigger force. So there is a resultant difference between in the vertical level, but there is no resultant difference for the horizontal level. The horizontal forces are simply going to cancel each other out in opposite direction. So that's the point that I wanted to make, that I wanted you to understand. And so this is what's going to happen. So this is why we actually feel lighter whenever we are submerged into water. So another way that I could possibly describe the upward force being available over here is that at the upper level, the pressure is less. At the lower level, the pressure is high. So if we just consider the buoyancy force, the downward force is going to be small, whereas the upward force onto the ball, because from the liquid, is going to be definitely bigger. So the resultant force is going to be this ash-colored arrow, which comes out as the upthrust. Now, whether this upthrust is going to be able to make the object rise and float, that is going to be another different question. That will be defined by the tug of war that Mark Rober used in his example, that whether this upward force would be able to make the object float or sink is exclusively dependent upon the comparison, keyword, comparison between this upward force and the weight of this object. So what happens for the next part of the video, what it shows up over here, is that here comes the video. So if we have a duckling over here, the duckling on the surface have a larger upthrust force than the weight, so it actually floats. And if you consider a bowling ball, it has a large weight compared to its upthrust. It does have an upthrust, but that is not the upthrust is smaller than the weight, so it is going to sink down. And then whenever he's using the idea for balloon, so he said in this part, I mean, have a look over here. I mean, this is the important bit.
Buoyant in our atmosphere. So here's a trick question. Which of these has a higher buoyancy force?
Which of these has a higher buoyancy force? Which means which of these two objects has a bigger upward force? Upthrust, which is bigger for which one? Now have a look at
It's actually the rubber ball. Buoyancy force has nothing to do with the density of the object.
This is the equation. Buoyancy force is given by, I mean, you are not going to deal with this equation, but I'm just showing it to you to make sense with you. Buoyancy force is given by the density of the fluid multiplied by the object volume into gravity. Now here, the density, I mean, for the example that he is showing right over here, fluid means the medium in which we are judging the two objects. That would be air. Both the rubber ball and the helium balloon, they were both kept in air. So the density of fluid density is same for both of them. But the volume of the object is different for both of them. The rubber ball was big in size, so it has a bigger volume, and gravity is essentially equal for both of them. So because the rubber ball had a bigger volume, it is going to have a bigger buoyancy force, and the helium ball is smaller in volume, so it's going to have a smaller buoyancy force. Wait a bit, I'll take your question in a while, just in a while.
Just the volume. So since the rubber ball takes up more space, it has a higher buoyancy force. But, you might object, then why does the rubber ball sink and the balloon floats? Remember, it's a tug of war. The rubber ball sinks because the force from gravity on the thick rubber skin and the air inside is bigger than the buoyancy force.
Try to understand.
But for the balloon, even though it doesn't have as big of a buoyancy force compared to the ball.
So have a look. In terms of buoyancy force or the upthrust force, this one has a bigger volume, this one has a bigger size arrow, this one has a smaller volume, this has a smaller upward force. But if you think about the weight of this object,
it still floats up because that buoyancy force is.
The helium balloon has a much smaller weight compared to the upthrust. So this one's weight is extremely small compared to the rubber ball weight. So the idea is about comparing these two forces. For the rubber ball, the upthrust is smaller than the weight, that's why it falls down. But for the helium balloon, the upthrust is bigger than the weight, that's why it rises up. But in terms of actual measurement of the upthrust force, the rubber ball has a bigger volume, so it has a bigger upthrust force, whereas the helium balloon has a smaller volume, so it has a smaller upthrust force. Kids, do you understand what I'm saying? The magnitude of the upthrust force will be
Yes,
determined
sir.
by the object's volume. But whether that will enable the object to go up or go down is going to be determined by the comparison of the upthrust force of that object with its own weight. So how much is going to be these arrows be is dependent on the volume of this thing. Is it going to move
Sir,
up
is
or
this
down?
comparison called the tug of war?
Yes, exactly that one. That's essentially what he showed in the tug of war. I mean, if I go for the tug of war part, here is Stone Cold Steve Austin. So this is the tug of war. So gravity was pulling, I mean, because he could not draw a vertical figure over here, that's why he showed this thing. The gravity is pulling in this direction, the air is pushing in the upward direction. So as long as these two things are perfectly balanced, you can have it floating. This is what he essentially showed for this case, that this ping pong ball was practically floating over here, because at this height above this air blower, hair dryer, the weight was perfectly balanced by the upthrust, so the ball was at equilibrium with a little bit of vibration. So it's not essentially moving, but it is not perfectly stable because the air is turbulent. So this is what is happening when the tug of war is exactly equal. But if you speed up this thing pretty strongly, then this is gonna flow upwards and eventually fall out of the vortex of the air. And it's gonna fall out. So that's what he showed by introducing Stone Cold Steve Austin, that if you somehow increase the upward force, or for his fluidized bed, if you increase the pressure of the air, then your upper air force is going to be bigger and the gravity is going to be smaller, and all of your stuffs are going to explode up. So that's what happened when he
Air up too high.
everything was exploding out, because that's the case where it was not balanced. So he had to do quite a lot of trial and error to find out the exact pressure or exact rate of airflow out of those pipes, so that he could make all of those grain particles perfectly floating. So that was a question of quite a significant number of trial and error, and he had to find out the sweet spot. Once he could reach the sweet spot, he could balance out the sand particles, each sand particle for their individual weight with the upthrust, and that's when this whole sand bath became moving like a fluid, because all of them were pretty much suspended in a free state. Do I make sense?
Yes, sir.
Yes, sir.
Yes, sir.
So two of you actually raised your hands. Did you just drop your hands? Yeah, Diafnan, go ahead. You had a question?
Sir, I sent it in in the chat.
Oh, okay, sure. I'll have a look. The bigger the mass, the smaller the upthrust. No. The upthrust is not dependent on the mass. The upthrust or buoyancy force, which the term that Mark Rober used over in his video, is dependent on the fluid density and object volume, not mass. Mass is going to determine how much is going to be the object's weight. So the weight is the downward force.
The fluidization occurs also as a function of the density of the surrounding fluid and the volume of.
Have a look. Buoyancy force or upthrust is dependent on the fluid density, which is the air, and the object volume is the object of the rubber ball or the helium balloon, or for the sand tray, it is the volume of each individual sand grain multiplied by the gravity. So the buoyancy force has to do with the volume of the object. The mass has to do with the weight of the object. So the question that you asked, the bigger the mass, the smaller the upthrust. The answer to your question is these two variables are not even related. The bigger the mass, the bigger is the weight. The bigger the volume, more is the upthrust.
So buoyancy force is basically exerted by the water or the liquid, right?
Yes. Diafnan, did I answer your question?
Yes, sir.
Yes, fine, good. So yeah, that's the idea for the pressure thing, which is a pretty interesting idea. I actually showed you this video to make sense with you, because I personally find this video really make sensing, sense making for the whole idea of upthrust and everything. It makes a very good animation and everything. So this guy is a very amazing video YouTuber, and I like his channel. I love his channel. Really love his channel. So আচ্ছা এই পার্টগুলোর কথাবার্তা বললাম, প্রেসার কথাগুলো বললাম. So this was an example. I mean, the reason I actually started talking about this because I wanted to elaborate the idea. I wanted to elaborate the idea of what do we mean by partial weightlessness. So whenever we submerge an object into a liquid, we might experience partial weightlessness for regular water. But then again, if you can achieve that sweet spot of upward air flow so that the weight of those sand particles perfectly it becomes equal to the upward force of the air pushing them upward, then you can essentially have them suspended. Suspended means it's not gonna rise up, neither is gonna fall down. So that can happen. This is also the mechanism by which hot air balloons work. Do you guys know what is a hot air balloon?
Yes.
For those of you who cannot make or if you just let me just show you. These are the hot air balloons. The way these balloons work is that can I get a single high definition image of a hot air balloon where I can see the burner? Okay, this is almost visible. I think this is gonna work for me. Is it gonna work for me? Okay. Open new image in new tab. Okay, so what is actually happening over here? I mean, the way these hot air balloons are made, this is entirely filled up with regular air, not by any hydrogen or helium gas. And then they have a burner over here. So what they are doing, they are burning up this fuel and heating up this air over here. So whenever the air is being heated up, it expands in volume. So because the mass of the air inside this balloon is constant, but you are increasing it in volume, so it is becoming less dense. So this entire balloon has a less dense fluid inside and a more dense fluid on the outside. They are both air, but this one is a high temperature air, and around we have a slightly cooler air, which is the atmosphere. Because this one has a high temperature air which has a lower density, this balloon can go up. If you stop burning this fuel, what's going to happen? Within significant amount of time, all of the heat energy that was absorbed to this balloon, they are going to be dissipated to the atmosphere, and this balloon is going to slowly start to lose height. So if you want to push the balloon upwards, you burn the fuel, make the air hot, and you're going to go up. If you want to maintain a fixed height, you provide heat energy to the gas every once in a while. Let's say after every 5 minutes, you're going to burn this burner for 10 seconds. Provide the heat amount that this inside air is going to lose to the surrounding during that duration. If you can do that, then you can maintain a fixed height. That is what was shown over here in this video, Markov video. Where is the Markov video? Yeah, what was shown over here by this colored figure where the balloon was getting stuck at a point in atmosphere. This one. So what he's showing up over here is a relative consideration of that variation of density of air. What you need to understand that close to the Earth's surface, the pressure of the air is extremely large. As we slowly go up and up and up and up and further up, the pressure of the atmosphere slowly decreases. So the density of the air slowly decreases. So this balloon this helium balloon has a much lower density than the bottom level of air. So it's going to start rising up. How long or up to which height is it going to rise up? It's going to rise up as long as this one's density and the surrounding air density becomes equal. So have a look what is happening over here. So
will eventually hang out where the and the helium will keep rising like a ball floating up from deep in a lake, and then it will eventually hang out where the density of the atmosphere is roughly equal to the density of the helium.
So in this case, he is trying to density is represented by color. So a darker shade represents a higher density, a lighter shade represents a lower density. So this helium balloon is going to get stuck at the level where the helium density and the atmosphere density become equal, and this is not going to rise up any further, because at this point the upthrust is going to become zero. No, upthrust is not going to become zero. At this case, the upthrust is going to become exactly equal to the weight. Bujo, Palaman. When the balloon was at the ground level, which of these forces was bigger, upthrust or weight?
Can you repeat?
When the helium balloon was located at ground level, near to the surface of the earth, at that
Yes.
point, which of the forces, upward force, which is upthrust, or downward force, weight, which of these two forces was bigger, or were they equal?
Upthrust.
Upthrust was bigger. That's why the object is slowly going up. Now, as the balloon is slowly going up, the surrounding air's density is slowly becoming less and less and less and less and less. And eventually, as the surrounding air becomes less, so the upthrust value is going to slowly become less. Why? Because come again, have a look at this equation. Where is that equation? I did just lose the equation. I think I lost the equation.
Higher buoyancy force. It's actually the rubber ball. Buoyancy force has nothing to do with the density of the object, just the
Have a look. Buoyancy force is depending on what? Fluid density into object volume into gravity. As the balloon is going to slowly go up, the fluid density, which means the surrounding air, that is decreasing. That was shown by the shade of blue color. So when that density becomes equal to the inside density, basically you will have the exact amount of weight equals to upthrust, and that's why the balloon is not going to rise any further. So that's essentially what is.
helium will keep rising like a ball floating up from deep in a lake, and then it will eventually hang out where the density of the atmosphere is roughly equal to the density of the helium in the balloon, because that's where the tug of war becomes equal.
That's where the tug of war becomes equal, which means this is the point where the upthrust and the weight has become exactly equal and opposite to each other. Does that make sense?
This is like the Fanos.
Beautiful. This is exactly like the Fanos.
Yes.
This is exactly what happens in Fanos. Fanos is a very crude version of a hot air balloon. We light up the fuel source, which heats up the air inside, and it becomes lighter. It starts to go up. As long as that lump of fuel, which is usually a wax, that has enough of wax available into that piece of cloth or whatever that is burning, this is gonna be going up and up and up. And at one point, the fuel might finish, and that's when the air is gonna start cool off, and it's gonna slowly start to fall down. That is one possibility. Or the other possibility is that the Fanush is gonna keep going up and up and up and further up, and eventually at the level of the atmosphere where the density of the inside hot air, it becomes equal to the density of the outside air. That's where that is the highest ceiling of the rising for the Fanush. It's not going to rise any higher because it doesn't have. That's exactly where the tug of war got finished. Yes. বুঝতে পারছি?
Yes, sir.
Yes, sir.
Kids, if you have any question, please raise your hand or ask me the question. This is a good time. Anyone?
Sir,
Yes.
sir, what causes less upthirst?
From the equation, the upthrust was, yeah, let me just write the equation. Upthrust was given by the density of the fluid into the volume of the object into G. So reduction, this is coming as the product of these three values. So reduction of any of these three quantity will give you a smaller value of upthrust. A smaller volume of balloon will have a smaller upthrust compared to a larger volume rubber ball. Then again, if you consider the same volume for the balloon in different levels of air, then the density of the air, density of the fluid is becoming less as the balloon is going into a higher level. So this person, Mark Rober, has shown us two different examples. In the first example, he's trying to compare at the same air level for two different volume of objects. One of the rubber ball, bigger object, and the was helium balloon, which is a smaller object. So for that example, the volume of the object was the variable. Whereas as the balloon goes higher up, that's where the density of the fluid, becomes what? Changed. because the volume of the helium balloon, because now we are considering the same helium balloon rising up at different levels. So that's the point where the volume of the balloon becomes constant, but the surrounding mediums, which is atmosphere's density, is becoming less. So that's why the upthrust is also becoming less. So any change of these three variables is going to give you a variation of upthrust, because they are all in multiplication form. So decrease of any of these variable is going to give you a decreased value of upthrust. Simple.
Sir, I had a question.
Yes. So before I take your question, whoever asked the last question, did I get your question answered?
Yes, sir. Thank you, sir.
Sure. Adiba bolo.
Sir, if the weight of the how does the weight of the ball becomes less when it's in water?
Because weight is given by mass of the ball into g. Even if it is in water, the mass of the ball does not change, the g does not change. So the product of these two variables does not change. Weight of the ball doesn't have to do anything in terms of where that object is located, how the object is oriented, or any such other thing. It is only dependent on two factors: mass of the object into gravitational field strength of that location.
Oh, so because it gets a bit higher, for that reason the weight of the object becomes a little less.
Well, to be honest, yes, but that change might be negligible. But yes, I'll say yes to your question. Yes.
Okay, sir.
Yes, Nuran.
Sir.
Sir, you said the volume of the air decreases. Sorry, the density of the air decreases as we move up. Does the temperature decrease as well?
Yes, the air essentially becomes cooler as we go up. So which means that if you consider for the hot air balloon, the rate of heat dissipation will become more rapid if you go into much higher level of atmosphere, which means you're gonna have your balloon cooled off much too faster, which means you have to provide the heating more rapidly, or
okay,
with small
thank
time
you.
intervals. Yes. Yeah. Yes, Tasnim Fariha.
স্যার আই হ্যাড এ কোয়েশ্চেন যে কখন দুইটা ফোর্সেস ইকুয়াল হয় যে আপথ্রাস্টটা
Upthrust and weight.
Yes, sir.
Upthrust and weight can be made equal by an artificial process, which he showed us for the fluidized bed, that if you apply a certain pressure for the air output so that the upward flow of the air balances out the weight, that is possible. Or upthrust and weight can be equal if you are somehow making sure that your entire object's volume is producing enough upward force that is exactly equal to the weight. So you can essentially make the upthrust and the weight in two different ways. I mean, if I just write up the equation over here, have a look. Let's say if we want W equals to upthrust, if I want to have this, W is going to be coming from the mass of the object multiplied by the gravitational force of that equation, and the upthrust would be given by the density of the fluid multiplied by the volume of the object into G. So I can essentially cut off G from both equations. So what you are essentially left with is that mass of the object will be balanced by the density of the fluid into the volume of the object. So if you consider these two parts of the equation, what this essentially tells you that if you want these two things to be equal, the product of these two things has to be equal to this one. Now, the reason I'm showing you an equation so that you can make a holistic understanding that what actually makes them equal. Well, you can have the volume go up with a small density, or you can have a small density with a large volume. Somehow the product of these two things has to be exactly equal to mass of the object, so that you can have these two things equated, and that's exactly when you can achieve weight equals to upthrust.
Okay, sir.
Okay. Hey, I'm gonna give you a break, but before I just go ahead, one of the boys was about to make a question. I forgot. I mean, you started the question, then you didn't raise it, so I asked one of the girls to ask the question. Who was the boy who was about to make a question? Someone was there? Was there someone? Maybe not. Okay, we'll take a break for 7 minutes. We'll resume class at 7:05. Break for 7 minutes for prayer.
Sir.
Yes.
I had a question that when the density becomes equal, like both from outside density and inside density becomes equal, what will happen next?
The upthrust would become equal to weight.
I mean, will the balloon go higher or lower?
No, that is the exact location where the balloon will get stuck. The balloon will get stuck at that location.
Sir, how can a balloon get stuck in the middle of the air?
By achieving equilibrium.
Sir, how does it achieve equilibrium?
By equating the upward and downward forces. By equating the upward and downward forces. I mean, let me give you a very simple example, which might as well make sense. You guys have seen an aquarium, right? Fishes can exist at different level under the water. How is it possible a fish can float in water at a specific level? It's the same thing with air as well, because at that level the fish manages the air volume inside its body such that the upthrust is exactly equal to the weight. That's why it doesn't fall down, neither does it go up. That is the exact same mechanism how submarines work. This is the exact same mechanism how hot air balloons get stuck at a certain level of the air. I mean, you can just simply replace the water with air and the fish with hot air balloon. That's exactly what happens. The two forces, upward and downward forces, become equal. So you have an equilibrium. So you don't have any resultant force on the object, and it can reach equilibrium. We never say.
Yes, sir.
Sure. So we'll take a break and we'll resume class at 7:05. I'm pausing the recording. So 5 minutes break. Yeah. So we are resuming class once again. I was answering some questions. So one of the questions that I did not answer in last class, which was from which I forgot the name of this kid. Ke jono question korsila? Orgho na, not Orgho. One of you kids gave me a question about the feather and the steel ball. Who was this kid?
Sir, it was me.
I cannot see your name.
Miss Ari Brian.
You are speaking through this channel, but why am I not seeing your microphone icon popping up? Acha, never mind. Maybe some Zoom bug, whatever. Acha, okay, Ari Brian, yes. So I'll try and answer that question. The reason I actually deviated this much to move out from answering your question into the whole idea of density, because this idea is going to be very useful. This idea that we have learned over here is going to be very useful for me to give you an explanation. Have a look. How fast is an object gonna accelerate downwards is dependent on how much resultant force does the object experience downwards. This is the key part that you need to understand. The resultant force is the moving factor. Not only weight, not only upthrust. How much is the resultant force? Now, there are two examples that I want you to understand. If we drop a steel ball in air for a short height, let's say 1 meter distance for a practical experiment, or 2 meter distance maximum. For that height, the air resistance that this object might experience is going to be extremely small compared to its weight. So this figure is not drawn to figure, but I'm trying to show the air resistance with a red arrow, for example. So the air resistance is going to be really small compared to the weight for a heavy steel ball or for a dense object. But if you consider for a feather, let's say this is a feather, looks like a leaf, but let's say this is a feather. So if you consider a feather is a really fluffy object. It's very light and it's less dense as well. So it has a really small weight to start with. So its weight value is extremely small. So as it is going to start falling through air, even after falling even a slight amount of distance, the upward force is going to become pretty much equal to the upthrust. The upward force of air resistance or drag is going to be equal to the weight. So this object might as well actually accelerate for the entire duration of the fall. It's going to speed up further as it falls. But this object, if you allow it to fall to the same height, is going to fall down. It's going to accelerate for a small distance as long as these two forces are not equal. The instant these two forces become equal, from that point further downwards, the velocity is going to be really small. It's going to be a small velocity. It's going to maintain its uniform velocity because the air resistance has become equal to weight. So that is the idea of tug of war that I wanted to get in your head, that when these two forces, upward and downward forces, become equal, object will either remain stationary or it will keep moving with the same velocity that it had earlier. So for the hot air balloon case that I just talked to you a bit earlier, for the hot air balloon, the balloon reaches equilibrium at a certain level of air being stationary there. So because the initial state was stationary, as the forces become equal, it remains stationary. It can float at a specific level of air, so you can go around, see the sights and everything. So that works. As for the feather experiences the equilibrium of forces after starting to fall down at a certain speed. I mean, if you keep the feather stationary in air, it's not going to have air resistance. Air resistance is a force that is only that is only available to us whenever an object is going through air, and as a result, air is only available to cases when an object is going through air and is colliding with the air particles. So after reaching a certain downward speed / velocity, the object is going to have the downward weight equal to the upward air resistance, and that's when the object is going to start falling pretty slowly. So if you drop both of these objects in air, essentially you'll see the steel ball is going to fall through the entire distance really fast, but the feather is going to fall pretty slowly. Now that's the first.
Is it because of the mass?
It's not because of the mass, it's because of the comparison of the upward and downward force for each of the objects individually. For the steel ball, the air resistance is negligible compared to its own weight. So comparing for the steel ball for its own forces, not comparing between these two objects individually, comparing the two forces working on a single object, upwards and downwards. Whereas for the feather, the two forces upward and downwards are going to be equal after falling to a short height, and from that point onwards, the object is going to maintain uniform velocity. So it's not because of the mass, it's because of whether the upward and downward forces working on the object does become equal, or how do they compare to each other.
But if we throw them at the same time from the same level
throw or
on
drop.
a place where
Hold up. Throw or drop.
Drop them.
Yeah, exactly. Let's use drop first. Yes, if you drop them from the same
height. Drop the two objects from the same height in a place which does not consist of air resistance, for example, space, then.
But we do have gravity.
Vacuum.
Yeah, we do have gravity. Will they follow? They will fall at the same time, right?
Exactly. If we do this entire experiment in an evacuated chamber where there is no air resistance, because there is no air, it's evacuated, means there is a vacuum inside. I mean, there is a vacuum inside means there is nothing inside, because vacuum means the absence of something. In that case, they are both gonna fall down really fast and hit the floor exactly at the same time with each other. And there is a very interesting YouTube video that I actually can show you. I'm showing you these YouTube videos to keep your memories fresh, so that you can refer to this information every once in a while. So hold up. This is the view that happened without the air resistance. The bowling ball is falling and the feathers are also falling, touching
so the mass is creating an impact.
Mass really doesn't matter, because I'll tell you why the mass doesn't matter. Have a look. I mean, I'll tell you. Let's finish. It's a large chamber which can be made evacuated.
This is NASA's Space Power Facility near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out the third. He took a heavy object and a light one and dropped them at the same time to see which fell fastest.
That's with air. Feathers are still falling because they reach terminal velocity.
Now in this case,
terminal velocity, word, terminal velocity where? Here, when the two things become equal. The feather reaches terminal velocity after falling by a very, very short.
Feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So in order to see the true nature of gravity, we have to remove the air.
Okay, we dropped 2 millitorr in the last 30 minutes.
But once it's complete, there's a near perfect vacuum inside.
6104 manual, 10% open. Station 1, go for drop. PCV 30-1, pressure set point at 240 psi.
This object from the holding point by using some electric switch, which is magnet, so you don't need air for that to operate, and they're gonna let go of those two objects at the same time.
Here, go for drop.
10, 9, 8, 7, 6, 5, 4. Cameras on, 2, 1, release.
No air resistance. Synchronized follow. This is just beauty, pure beauty. So that's the point. Now, some of you might actually wonder, so if the feather has a much smaller weight or mass compared to the ball, if this one has gonna have a bigger force, this one's gonna have a bigger force. So shouldn't this one experiencing a bigger weight fall faster? Well, here's the catch. How fast does it fall is not dependent on the downward force. How fast does it fall is defined by acceleration. This is what defines velocity. This is what defines motion, not this one. Important fact. Let me elaborate what I'm trying to mean. Once you define the resultant force on an object by its mass, you get the acceleration of the fall. This is what gives you velocity. This is what gives you motion. Now, for the large ball, the weight is large. The mass is also large. The division gives you the gravitational acceleration. For the feather, the weight is small. The mass is also even smaller. So the ratio still gives you the same gravitational acceleration, which means both of the objects are going to be subjected to the exact equal amount of acceleration. So they're going to speed up at the same rate. They're going to cover the exact same distance over the same amount of time. They do have different masses, which gives us different value of weight. But bigger,
they will be having the same acceleration.
They will have the same acceleration. Bigger force is accelerating bigger mass, and smaller force is accelerating smaller mass. But the ratio of force divided by mass, which gives us the acceleration, is exclusively equal for both of them, exactly the same. That's why they fall synchronously. বুঝাচ্ছে?
Yes, sir.
Yes, sir.
So, Arif, did I make your question clear?
Yes.
Do you understand that why?
Resultant force of the feather equal হয়ে যাবে if I
equal, I mean in vacuum?
না বাতাসে
হ্যাঁ বাতাস থাকলে ফেদারের ডাউনওয়ার্ড আর আপওয়ার্ড ফোর্স ইকুয়াল হবে, বাট বলের জন্য হবে না।
কোনো ডাইরেকশন থাকবে না স্যার, ফেদার কোনো পার্টিকুলার ডাইরেকশন থাকবে না।
Well, it's falling downwards. It's falling downwards.
কিন্তু দেখা যায় যে ফেদারটা কিন্তু বাতাসের মধ্যে ফ্লোট করে।
হ্যাঁ
কিন্তু দেখা যায় তাহলে
it floats, but it ultimately lands on the ground. So the direction of velocity is essentially downwards. I mean, it does not float and eventually start to go up unless you have an updraft. If you do the experiment in still air, not wind, okay, then the feather is definitely going to land onto the ground.
Okay,
but it's going to take longer, definitely much too longer compared to the steel ball which we just saw in the video.
Achha.
So do you understand that why, do you understand understand the context that why before I explain this one I go through all of this explanation? I mean, do you understand the link between these two things? Do you? Someone or all of you?
Sorry sir, but I'm confused.
Okay, if you have any idea, anything, you are allowed to be mistaken. That's what the class is about. Write down in the chat box what you think is the relationship of these two explanations. I mean, why did I bother to explain all of this stuff before explaining this thing? Why did I want to do this first and this one later? Write this down in the chat window. Everyone, go ahead. Whatever you think.
Sir, I had a question.
বলো।
স্যার মনে করে দুইটা ফেদার আছে, একটা হচ্ছে লার্জ ইন সাইজ, একটা হচ্ছে স্মলার ইন সাইজ, তো ওই দুইটার মধ্যে কোনটা সবার আগে নিচে ল্যান্ড করবে?
উইথ এয়ার অর উইদাউট এয়ার?
উইদাউট এয়ার, মানে খালি জায়গা।
উইদাউট এয়ারে সবাই একই সময় ল্যান্ড করবে, বিকজ উইদাউট এয়ার there is no upward force. All that you have is the downward force weight, which is going to create equal acceleration on all the objects irrespective of their masses. In vacuum, every object, less mass, big mass, dense object, light object, doesn't matter, everything is going to accelerate downwards at the same rate, g, 10 meter per second square. So I have two expressions from two people. I mean, the rest of you, 41 other people, do you not understand the relationship of these two? You're allowed to write whatever you feel like. Write publicly so that everybody can see your expression. You don't have to individually say me. I mean, this is a discussion class, so all of us, including me, are allowed to do mistakes, and we can cross-check it by discussing among each other. So it's perfectly good. Anyone else? I have like 10 expressions. Okay, for those of you who have written all these expressions, all of you are correct, to be honest. I mean, you have individually sorted out different aspects of the comparison, and my aim was primarily to give you an idea that what do we mean by equilibrium, because we're going to cover that part in our next topic in the motion chapter, that what do we mean by equilibrium. Equilibrium means the resultant force being zero. In that scenario, individual forces doesn't play a role. Summation of all the forces play the role. That's the first idea I wanted you to have. So what I'm trying to mean, that whether this ball was going to go down or up, whether the rubber ball is going to fall downwards or the helium ball is going to go upwards, what actually defines that behavior? It's not exclusively the weight, neither is it exclusively the upthrust. It is about the sum of these two forces. This is important for you to understand what is happening here. When the air was present in our chamber, the upthrust, the air resistance of the steel ball was negligible. So the weight was a significant force. So it fell down really fast, accelerating all the way. Whereas the feather actually came to equilibrium of forces / terminal velocity after falling a little bit, and then it maintained that velocity and slowly floated through air and eventually fell down on the ground. And then whenever you make the entire chamber nearly vacuum or almost vacuum, and you allow both of them to fall downwards, you do not have upward force anymore. Then the only available force is the weight, because weight does not require atmosphere to work about. Any two object that has mass will experience the gravitational force. You don't need any medium in between to work that. So the weight will be exerting on both of the force, and they are both going to be accelerated by 10 meter per second per second. So that's why I discussed this part first, to give you an idea of what is equilibrium, how the equilibrium is created, what to compare to get the idea of equilibrium, and then I went into this idea, so this would be easily understandable for you. Hold on, বুঝা যাচ্ছে কি?
Yes, sir.
Yes, sir.
Yes, sir.
জি স্যার। কার কোনো কোশ্চেন? এনিওয়ান? If you're clear with this one, please write yes. I mean, I just need to make sure that you kids are here. Just write yes in the chat window or respond in the chat in the voice channel.
Sir,
I'm
Yes.
still a bit confused.
sir,
Yeah.
could you explain the formula that you wrote? W by M equals to G. That formula, that part.
Oh, this is basically F equals to ma. That is the general second law of for Newton's law, which we're gonna definitely cover in our next class. So it's a bit far-fetched. This is the second formula for resultant force. I should definitely give the resultant symbol. So if you consider weight for an object, W equals to mg. Weight equals to mass into gravitational acceleration. So if you divide the m over here, you get this one. So big weight divided by big mass gives you g. Small weight of feather divided by small mass of feather gives you the same value g. That's what I meant.
Sure.
Same value as in both of them have the same value.
For acceleration, they'll both have the same value, but they're gonna have different values of weight because they have different values of mass.
So sure, what is the relationship between both of them? Is it the sum?
The relationship in both of them in vacuum is that in vacuum, the upward force simply does not exist. So the downward force can be different for each of them, but that force would accelerate them by the same rate. So when the upward force air resistance is absent, all objects, big or small, wide or thin, less dense or more dense, they're gonna all fall downwards with the same exact value of acceleration, that is the value of g. They're not gonna have different acceleration because we do not simply have the upward force available anymore, which means all of them are gonna have only one force working on them, that is their weight. Now, more massive objects are gonna have more weight, so less massive objects are gonna have less weight, but the ratio of their individual weight divided by their own mass, that ratio is gonna always be 10 meters per second squared. That's what I meant.
Always.
Always. All right. It's about 7:30, and I am not going to start a new chapter, a new topic today. But just to give me an idea for next class, we're going to start in our next class equations of motion. Equations of motion. Just remind me of this name. We're going to start with equations of motion, and we're going to see some calculation and the implication of those calculation. I mean, basically, in our last class, I actually explained the physical implication of the acceleration. I showed you how the velocity of a upward thrown ball is going to vary at individual time instances. We did some calculation about that. Do you remember? I mean, we threw a ball vertically upwards, it was going up and slowing down. So we did calculate what would be the velocity of that ball at different time instances. Do you remember?
Yes, sir.
You should. If you don't,
Yes, sir.
you might as well see our last lecture for a quick recap. So we did that calculation by using our concept, by applying the idea of acceleration. And next class, we're going to see how can we do all of these things in a much simpler, faster way by using equations of motion. So we're going to pick that up in next class. Everyone, thank you very much for waiting because I was late, and thanks for your attention. If none of us have any more questions, we're going to call it a day.
Allah Hafiz, sir.
Bye, sir.
Yes, sir. Thank you very much.
Bye, sir.
Bye bye. আমি একটু পরে লেকচার আপলোড করে দিচ্ছি, যাদের কোনো পার্টে বুঝতে সমস্যা হয়েছে একটু দেখে নিও, নো বিগ ডিল। বাই, আল্লাহ হাফেজ, থ্যাংক ইউ।